advanced biofuels. Unlike the first generation, advanced biofuels don't use food or feed as a resource. In fact, using advanced biofuels from sustainable biomass means cutting CO2 by at least 70% compared to fossil fuels. So why don't we use more? Like all breakthrough technologies, advanced biofuels have high initial costs, and policy uncertainties of the last decade have had a detrimental effect on investments. The new Renewable Energy Directive is going in the right direction, but stronger support is needed to increase the confidence of investors and boost research activities. This is the best way to speed up the use of advanced biofuels and reduce the carbon footprint of transport.
Okay, so good afternoon, everyone, and welcome to this Advanced Fuel Policy Briefing, exploring how can Europe develop a market for advanced renewable fuels. My name is Simon Hunkin. I'm working for an organization called Greenaway Europe, which is responsible for communications in the Advanced Fuel project. I will be your moderator for this afternoon's session. I'd like to start by thanking you all for attending today. We've had more than 100 registrations for this session. So certainly it's one that's been quite attractive and has attracted quite a bit of interest. And I'm looking forward to quite a lively panel discussion with you all later on. The Advanced Fuel project began back in 2017 with the aim of identifying barriers to the uptake of renewable liquid fuels, aiming to build a knowledge base to help stakeholders make informed decisions for supporting market development. Today you'll hear from our project partners, who will outline their main achievements with information and recommendations along the entire ResFuel value chain. I won't provide any more information at this point on the project itself, as our project coordinator will provide a brief overview shortly. But I do want to start with a few of the technical housekeeping points. So this on the screen is how you will see your control panel. You'll see that there's a space there for you to submit questions. So we'll be taking questions in written form throughout the full webinar, so please do submit at any point. I would like to ask though for a little bit of assistance from you. So basically, if you are submitting a question for clarification of something that you've seen in a presentation, please submit that question with an exclamation point at the beginning. This is just to help us to notice it and to make sure that it gets asked immediately after the presentation. All other questions will be saved for the panel discussion towards the end of the webinar. Any questions that we cannot answer during the webinar, perhaps we will run out of time, we will attempt to tackle by email. And finally, because it's a question that we always get asked, yes, this webinar is being recorded and you will all receive a copy of this video after the webinar is over. So without any further interruption, let me introduce our first speaker. This is Kristin Sternberg, who I have made presenter now. He was the coordinator of the Advanced Fuel project from the Agency for Renewable Resources in Germany, or as it's better known, FNR. So Kristin, as I said, has been the project manager of the Advanced Fuel project and will give us a short introduction now of the project's approach. Thank you, Kristin, over to you.
Well, thank you very much, Simon, for the kind words and the introduction to myself. Yeah, a warm welcome from my side as well, as being the coordinator of this interesting project. I think I need to bore you a little bit with some introductory slides on the project itself. Maybe some of you have heard this several times, so I apologize for this, but I will be quick, and for some of the new attendees, this might be needed. So the Advanced Fuel project. As Simon has already mentioned, we already started our work in 2017, and the project is close to its end, which will be in August. And it is actually a coordination and support action, which is funded by the Innovation and Research Program Horizon 2020. And it assembles 8 partners from 7 different countries, as you can see here on the map. They are mainly leading research institutes or universities. And the project is coordinated, as Simon already stated, by FNR, but we get strong support also from the Dutch Energy Research Center, which was ECN, is now TNO, represented by Ayla Uslu in this project, and who coordinates all the technical or scientific work. Okay, to the background. The background of the project, well, I think I can say it's mainly the climate change and the debate that evolves around it, and the mutual agreement on the necessity to reduce greenhouse gas emissions. And this seems to be rather important, particularly for the transport sector, as this is the only sector where the emissions are still increasing. And so some more some more efforts have to go into this attempt to reduce further emissions, and this needs to take place with multiple approaches, as we already found out, by, for instance, increasing efficiency, by further developing technology, and but also also for with electrification. But this can't be done for all the transport sectors involved. This is particularly true for the shipping and aviation sector, as well as the heavy-duty vehicle sector, where we actually, at least for the short and medium term, we need advanced or liquid, ideally a liquid advanced renewable fuels. But there is a problem still, because there's still not enough of these sustainable fuels on the market. And that's where ADVANCEFUEL comes on the scene, as our mutual goal is to support the further commercialization of these fuels. Next slide. Good. Some words on the project scope. We actually concentrate our work when I talk about advanced renewable fuels. I actually mean liquid fuels. We agreed on this, and we concentrate here on advanced biofuels, which are based on lignocellulosic feedstock. So no competition with food and feed markets. And we also included other renewable fuels that are produced from renewable hydrogen and carbon dioxide streams. And another important aspect of the ADVANCEFUEL project is that we actually consider the whole value chain of these fuels. So starting with the feedstock production, the whole logistics, as well as the conversion technology and the different end-use scenarios. So to sum everything up, I will just show you the whole slide. We formed activity groups around these different topics, following or the value chain steps. So starting with biomass availability, conversion technology, and so on. And we investigated, or our respective experts investigated these topics in detail to determine the barriers and gaps. And then, of course, our goal is to develop strategies to overcome or at least reduce those. And this eventually led to an integrated analysis of the findings to identify the most promising pathways for RES fuels. And furthermore, also we developed a decision, or several decision support tools for the stakeholders, as well as policy recommendations for the policymakers. Next. No, sorry. It's a bit of time delay. Excuse us for having these problems. Okay. As I said before, we are quite an academic consortium. As I said, we are mainly consisting, or the partners are part of scientific or leading research institutes as well as universities. But before you think it's quite a theoretic approach, we actually made sure to always have the link to the real market players, and we did this in several different ways. For instance, we established a stakeholder platform, and they are the registrants were always part of consultations and interviews to actually verify our findings and to make sure that they are actually relevant and true for getting realized on the real markets. Furthermore, we have a really experienced advisory board, which has supported us our work throughout the previous 3 years. So that was very, very helpful. And we also had very close links to other EU projects, where we had a frequent exchange, as well as to the European Technology and Innovation Platform Bioenergy, as you maybe know, and of course they have very strong industry links as well. So this is, I think, enough for a short introduction to the project, and now I think we can dive into the final results and our findings of the project. So have a good session, and we'll meet again during the final panel debate.
Okay, thank you very much, Kristin, for that introduction to the project. We've started getting questions already, but I see none which are for immediate clarification, so we'll save those for later on. So as Kristin has said, the ADVANCEFUEL project has started with an assessment of the current barriers to res fuels, setting the framework for the rest of the project work. And as such, this leads very nicely into our next presentation, which will be given by Ayla Uslu from TNO Energy Transition. So Ayla is a senior researcher at TNO with experience in energy transition and renewable energy policy analysis, with specific expertise in the analysis of the contribution of biomass and bioenergy in meeting climate policy objectives. So Ayla, as mentioned, has been the technical coordinator of ADVANCEFUEL, as well as leading work on barrier identification, and she has also been responsible for our work on scenario definition to 2050, which she will also very briefly present. So Ayla, please, when you're ready, the floor is yours.
Thank you for the kind introduction, Simon, and again, welcome to everyone. As the title of my presentation tells, I will briefly introduce you the market status of biofuels and advanced biofuels. I will touch upon the future demand for these fuels, and then I will share with you the identified barriers to advanced biofuels as validated by the stakeholders, and then set the scene for the following presentations. In this slide, I would like to share with you the renewable fuel consumption in Europe for the years starting from 2015 to 2018. The figure illustrates the numbers related to biofuels, conventional biofuels, the ones that are produced from food and feed-based crops, biofuels produced from Annex 9 of the Renewable Energy Directive, and also renewable electricity use in transport. When I will be mentioning quite a number of times Annex 9, Part A and Part B. For the ones that, for the colleagues who do not know them, actually there is an annex introduced to Renewable Energy Directive, and it includes a list of feedstocks, and Part A mainly relates to residues and waste from lignocellulosic feedstocks, but it also includes some other feedstocks like manure, and Part B relates to used cooking oil and animal fats. As you could see in this graph, by 2018, according to Eurostat data, Europe could meet around 8% of its transport fuel from renewable sources, but that 8% includes double counting. In energy terms, the total amount that meets is around 6%, and the majority is coming from conventional biofuels. Biofuels from Annex 9 relates to 1.3% of the total fuels, and among them, actually, majority, more than 90%, relates to Part B, and Part A is quite small, 0.2%, which is the focus of our project. Here, I briefly show you RED II, Recast Renewable Energy Directive, which sets the framework for the coming 10 years. As you know, there is a renewable fuel target for transport, which is 14%. This target includes multiple countings, as highlighted in the figure. There are caps and minimum targets. Caps relate to conventional biofuels, which is 7%. Another one relates to Part B type of biofuels, FAME and used cooking HVO from used cooking oil and animal fat, which shouldn't be more than 1.7% of the total fuel. And then advanced biofuels produced from Part A has to reach to 3.5% by 2030. It includes multiple counting. When this is excluded in energy terms, it needs to reach to 1.75% of the total demand. Also, when biofuels are used in aviation and maritime, they can be counted 1.2 times to the set targets. Here already you could see that there is quite a gap from today to reach 2030 targets. However, Advanced Fuel Project does not only look at the 2030 perspective, but concentrates on the 2050 perspective. And before I go into the details in this slide, I want to share with you the advanced biofuel total capacity in Europe. This figure illustrates the operational, under construction, and planned facilities that use lignocellulosic feedstocks. What is interesting in this slide is that, as you can see, the plant facilities, the total cumulative installed capacity of plant facilities are 4 times the facilities that are either operational or under construction phase. As you can see, within the operational plants, the largest total installed capacity relates to HVO produced from tall oil, and they are located in Finland and Sweden. The plant capacity within HVO relates to one company, actually, in Finland, UPM Biofuels, which aim to produce around 500,000 tons of HVO for the coming period. The next largest operational plants relate to production of pyrolysis oil, and they are in the Netherlands, Finland, and Germany. I shall mention here that the pyrolysis oil, for instance, produced in the Netherlands is currently not used for transport sector, but to produce heat, and their further use in transport needs some further processing. There are 2 pyrolysis plants under construction. One is in Finland and the other one is Sweden, each having an installed capacity of 24 kilotons. The current production of lignocellulosic ethanol relates here in this graph to 8 different demonstration plants that are located in Norway, Sweden, Finland, Germany, and France. And while most of these installations produce ethanol from agricultural residues like wheat straw and corn stover, they are all in quite small installed capacities of some hundreds of tons. And among these operational plants, there is only one that is first of a kind plant, and it is in Norway. There are two installations that are currently under construction. One is Romania using Clarion sun liquid technology with a capacity of 50,000 tons. Another one is in Austria with a installed capacity of 30,000. The facilities in this category actually also includes beta renewables, which is constructed, which was operational for some years, but it's shut down. As the figure illustrates, while there are no operational facilities based on gasification, there are quite a number of plants within this category. And among these plants, it's interesting again to observe that a large amount relates to waste to methanol plants. And so the feedstocks considered are mixed waste, which includes both bio and non-bio part, and non-bio part mainly relates to non-recyclable waste. Two large projects are at the planning stage. One is in the Netherlands and the other one is in Spain from Enercam. Within this category also we included Gobigas, which is again a gasification plant producing SNG, which was operational but currently shut down. As my colleague said, in addition to advanced biofuels, we looked at the e-fuels. And according to our study, the total installed capacity of e-fuels is around 6 kilotons, with two facilities dominating this. One is in Iceland producing methanol, and another one is in Germany producing methane. When we add all these installation capacities together, we end up with a figure of 2 million tons of production capacity. When we convert it into the energy content, I mean, we see that they can meet less than 1% of the transport demand in the coming period. However, as I mentioned before, RED II requires a target which is in the range of 200 petajoules. As I briefly mentioned, our project did not only focus on 2030, but beyond. And as Kristin mentioned, transport sector is the only major EU sector where greenhouse gas emissions are continuously increasing. And significant efforts need to be done, not in all energy sectors, but in transport as well to contribute to Paris Agreement goals. Within our project, we defined two specific targets for that. We considered an 85% CO2 reduction by 2050 compared to 1990 levels for transport sector, where international maritime is not included. For the international maritime, in line with the IMO strategy, we defined a 50% reduction by 2050 compared to 2008 levels. There are different ways to achieve these targets, of course. However, in our study, we wanted to define the order of the magnitude demand for RES fuels. So we defined two scenarios to looking at the future and focusing on technology development. We said, on the one hand, direct electrification of road transport using renewable electricity could be the main player in reducing CO2 emissions, and other fuels can play a complementary role. On the other hand, biofuels could be deployed significantly. The technology development could be quite well, and they can play the major role. Based on this simplified description of scenarios, we quantified the future renewable fuel demand, and this graph presents these demand figures, and the names are I think they are self-explanatory: road zero and transport bio. As you could see, Road Zero relates to a future where electrification is very large. The blue bar represents the electrification, and the biofuels appear to be relatively small, but I will say it cautiously that small is still quite large. It's around 1,600 petajoules. And in transport bio, you could see that biofuels play a major role, and electrification is still a significant component. But also in both scenarios, e-fuels and hydrogen are needed, and we say more is needed. And I would like to provide you, two takeaways from these scenarios. One is that regardless of the future policy preference, biofuels will continue to be a key component of reducing CO2 emissions. And another one is, for instance, in Road Zero, the progress in biofuels is limited. If and when the progress on technology development and also mobilization of resources is progressing slowly, you will need more expensive other options. In this case, it is e-fuels, and you will put the pressure to the power sector. Here in this graph, I detail actually, the first one relates to biofuels in general, whereas it represents the different categories of biofuels. First of all, biofuels, according to our scenarios, can play a role in the order of 20 to 55% of the road and rail energy demand meeting by 2050, and advanced biofuels is around and above 70% of that demand. And you could see that the increase from the current operational plans and construction, all the cumulative capacities, comparison to the future, you will need around 25% to 75%, 75 times, sorry, not percent, increases will be needed in the coming years. And these bars highlight routes related to biochemical conversion, mainly lignocellulosic ethanol production and its conversion to alcohol to fuels. And this bar relates to pyrolysis and hydrothermal liquefaction, whereas this large bar relates to advanced biofuels coming from gasification routes. Okay. Now moving to the barriers to market uptake, we already acknowledged that there needs to be a significant deployment of advanced biofuels. However, that there exist barriers, or let's put it, challenges to their market uptake. Kristin already highlighted that we covered the complete value chain. We focused on feedstock supply, conversion step, end use, also a cross-cutting issue, sustainability criteria. We made a long list of barriers based on literature and discussion with experts, and then we validated those barriers with the stakeholders through stakeholder consultations. On top of that, we asked them to prioritize the barriers so that our colleagues in the next stage can address them. And I will be sharing those barriers with you. When we look at the feedstock production, the key barrier mentioned is the high cost of feedstocks. It's quite understandable, as it is one of the components that play a significant role in total production cost of biofuels. And in addition to that, lack of clarity about environmental constraints and land availability has been highlighted as an important barrier in the supply part. And moreover, lack of harmonized regulations, mainly for biomass residues, both forestry residues and agricultural residues are mentioned. And this is quite understandable, as the sustainability criteria originally was set up for more conventional biofuels and related feedstocks. When we move to the barriers related to the conversion stage, again, the highest priority barrier has been the economic one. It relates to the high upfront capex cost. This also relates to the fact that capex comprise around typically 30 to 40% of the total production costs, and therefore any reduction in capexes are needed. Related to that, absence of dedicated policy support and access to project finance is mentioned, and concerns on stability and security of the industry for the coming years is mentioned as well as an important barrier. For the end use part, high production costs compared to fossil fuels is the main challenge to overcome, and related to that, absence of structural mechanisms to bridge this price gap between renewables and fossil fuels is mentioned as an important barrier to tackle. And within the sustainability discussions, clarity for sustainability requirements for the feedstocks suitable for lignocellulosic feedstock is mentioned as a concern, and sustainability criteria and certification for lignocellulosic biorefineries is also highlighted by the stakeholders, as sustainability criteria has been for biofuels, expanded to energy production. However, biorefineries produce also other products like bio-based products. And last, lack of harmonized regulations are mentioned as a challenge to overcome in the coming period. Okay, I cannot go to my next slide somehow. Oh yeah. Question is, okay, how are we going to address those barriers? I would recommend you to keep following and listen to my colleagues. Thank you for your attention.
Okay, thank you very much for that, Ayla. We've had 2 questions come in for clarification, so perhaps I can put you on the spot for a second.
Yeah.
The first question we have had is asking, in relation to the production of e-fuels in Germany, what exactly is the product?
It's methane. Actually, it is the name of the company is Audio E-Fuels, I think, if I hope I remembered correctly, and they are using CO2 from an adjacent biogas plant and combining it with hydrogen to produce methane.
Okay, thank you.
Yeah.
And the second question, to put you on the spot, is coming from Eric van der Heuvel. And it says, if the RED II target is 200 petajoule, how much does this relate to the 2 million ton of production that you mentioned? How many petajoule does that represent?
Oh, good question. It is around 60 petajoules, but I would like to be careful with this number, as I mean, gasification route, for instance, produces SNG, and it can be used for many reasons. Also, the pyrolysis oil, it's an oil. I mean, you have to upgrade, and therefore this number I would say plus minus, but it's 6 petajoules, which meets around 0.5% of the demand.
Okay, great. Thank you very much, Ayla. We'll move on to our next presentation now. So as the scenarios briefly presented by Ayla showed, the availability of biomass will be a major determiner of just how much biofuel we can produce in the future. In this scenario analysis, we had both the high biomass availability and low availability scenarios. So in this next presentation, we'll look more in depth into the biomass availability. And for this, I'd like to welcome both Vera Concha and Sonja Germer. So Dr. Sonja Germer is working at the Leibniz Institute for Agricultural Engineering and Bioeconomy, perhaps better known as ATB Potsdam. And Vera Concha holds a master's degree in sustainable development, is a researcher at the Copernicus Institute of Sustainable Development at Utrecht University. So without further ado, Sonja, please begin when you are ready. I will give you the control. Please begin.
Okay, thank you for your introduction. So we aim at highlighting ways to remove barriers for feedstock supply. We concentrated here on dedicated cropping of lignocellulosic crops, as for example, poplar, willow, or miscanthus, as you can see here. Barriers mentioned before were feedstock costs, which are directly related to feedstock yields per hectare, and doubts on the sustainability and land availability for feedstock production. But first, let's have a look at the current supply. There are no official statistics for dedicated energy cropping in Europe right now, but there are respective numbers in the Bioenergy Europe statistical report you can see here. The numbers are not accurate and might rather underestimate the real cropping area. According to this report, we have only 0.1 million hectares that are used for dedicated energy cropping right now. From the decarbonization scenarios presented in the second report, we can see that the demand of cropping in 2050 is estimated to range from 9 to 29 million hectares. And it's easy to see that there is a clear gap between suggested demand and today's production. Consequently, we need more feedstock and preferably at low costs to make it profitable. To increase feedstock production per yield, the yield per hectare can be increased, and the total area to be cropped can be increased as well. In deliverable 2.2 of the Advanced Fuel project, we therefore described innovations in lignocellulosic biomass cropping in terms of their potential to increase yields and reduce production costs. In some cases, the reduction results directly from yield increases, as is the case for irrigation of short rotation coppices with wastewater that was found to increase yield by 25 to 30%. In contrast, breeding to allow future miscanthus planting by seeds instead of using subsurface stem parts, as done currently, is expected to reduce biomass production costs by 7 to 16% due to reduced input costs. Breeding for increased resistance or water use efficiency, as well as fuel sludge application are other options to increase yields and decrease production costs. There are plenty of options for biomass producers to choose between species and varieties, management options, or to follow several purposes at once. Even though there are guidelines for short rotation coppices cultivation, these are no substitute for long-term experience. What worked so far is if there is an organization that guarantee purchase and advice for field as well as crop selection and crop management. And this is in line with one Swedish study we found of willow short rotation coppices that claimed that the learning effect might in future reduce biomass production costs by up to 25%. So they aim to increase biomass production while avoiding competition to food and feed production leads to the question, how much biomass can be produced on marginal land in Europe? Marginal land, that is land on which cost-effective food and feed production is not possible under the given site conditions and cultivation techniques. So such an assessment requires looking at the sustainable potential of biomass production on marginal land, but it also needs to consider the question on how much yield can be obtained from marginal land. If you try to answer this question using published data as compiled in this database, for example, we see two things. First, we realized that not many studies reported biomass yields from marginal land so far. And second, that there is a tendency for less average yield for marginal land than from non-marginal land. There is, however, no universal definition of marginal concerning the indicators. Here, we did not use the indicators of marginality pointed out by the authors themselves, as for example, degraded land. But we just used the location indicated in their papers and combined it with the marginality map produced by the MAGIC project, which also includes other indicators as climatic factors, for example, the length of the vegetation period. Here we have slightly more studies in the marginal land class, and yield difference seem to be less, but are still existent. So certainly average yield depends on the location, and this leads me to the next point. Please, Ivan.
Thank you, Sonja. Thank you for your presentation. Good afternoon to everyone. And now I'm going to continue the presentation, and I'm going to start talking about land availability and biomass potentials in the marginal lands that Sonja has been discussing about. So in the ADVANCEFUEL project, we applied the sustainability criteria of the RED II to a case study for lignocellulosic energy crop cultivation in the EU. Sorry, it's a bit delayed, the slides. So applying RED II criteria, we could identify if this criteria was effective to avoid negative impact of our energy supplies, while also providing insights in how sustainable were the supply potentials under this criteria. For now, I will focus on land availability and biomass potential, but we also estimated the environmental impacts, which I will present in the latter presentation. We need to consider that we did this in an aggregated approach just to include, like on a latter step, so what is the land availability? What is the biomass potential that can be yielded in this land that is recognized as marginal and meets RED II sustainability criteria? And later, what are the environmental impacts? We did this for the 8 of the most important lignocellulosic crops for the EU, and we did it for different points in time. So this way we could track what will be the projections to the future, and also to take into account the possible land use dynamics in the European Union. So now here in this slide, you can see on the left side 2 examples, because we have, of course, maps for every crop and for every point in time, and you can get there as quite some results. But here just an example of, to the left side, you can see the available land or available marginal land under RED II criteria. And on the other side, you can see the biomass potential that can be actually produced in this available land. So in top of my mind, it comes that there's around 205 to 210,000 square kilometers that are available in the European Union between 2020 and 2050 that can be used for producing this biomass. However, when we consider the crop phenological characteristics and other location-specific biophysical conditions, this amount of land that is available reduces quite some, and it reduces in almost 1/3. So you can see that a lot of the areas that were available before in the Scandinavian region, in the Baltic states, also in the Mediterranean, now all of them, they have been areas that you cannot produce because the conditions are not ideal, either for the crops or from the climatic side. And now I want to show you how does it look for potentials. So here it's a graph, and you can see on the x-axis, you can see the different points in time, and on different colors, you see the different crops that we assess. And on the y-axis, you see the petajoules or biomass potential. And you can see the 8 different crops. And on red, you can see something that we define as the yield efficient biomass potential, which actually calculates for each specific available location. It takes the highest yield, regardless of the crop type. So the red one, it's a combination of the highest yields for all the crops. The difference between crops is mainly attributed to either crop phenological characteristics or location-specific biophysical conditions. So for example, giant reed, where you can see it's one of the lowest, has one of the lowest biomass potentials, but on the opposite side, it's one that delivers the highest yields. But given that it has very restrained tolerance to different biophysical conditions, it can only be produced in several low locations, while the opposite occurs with reed canary grass, for example. So reed canary grass, that is one that delivers the lowest yields, can be produced in several locations in Europe, and therefore we obtain a high biomass potential. Just to give you an example, we estimate that for 2050 there's a biomass potential of 1,600 petajoules in total, and this is on the lower end of what other projects, and also in this project we have done with a literature review, we have estimated. So in other projects we estimate that the biomass potential in EU28 is around 4,800 petajoules for 2020 and around 8,200 for 2050. So it's on the lower end. And if we compare with the amount of land that my colleague Sonja was saying at the beginning, that will be needed between 9 to 29 million hectares in 2050. If we now consider the biomass potential of 2050 from the whole lignocellulosic energy crops, it comes around to 7.6 million hectares. So it's still on the lower end, but it's almost what has been indicated. And with this, I want to come up to some conclusions. So there's still potential to increase biomass yields for lignocellulosic energy crops. But for this, we need to implement suitable crop schemes. We need to include this type of spatial assessments because they need to be considered for decision making in order to maximize benefits from biomass production in the EU. As you can see, we need to consider where and what needs to be produced in order to maximize these benefits. And by the end, we need to use the marginal land for lignocellulosic energy crop production because it's a valuable strategy to cover to some extent future biomass demand. But this will also require quite some efforts to develop infrastructure, farming experience, regulatory compliance, and support, as well to enable a sustainable biomass production in the EU on the RED II. Thank you.
Okay, thank you very much, Sonja, Ivan. So we had one question come in for clarification, but it's related to the Renewable Energy Directive and indirect land use change issues. So I think that we'll cover that in a later presentation. So maybe we don't need to discuss that now. So thank you very much.
Okay.
Next up, I would like to invite Professor Stavros Papadokonstantakis to join us. So Stavros is Associate Professor in the Energy Technology Division of Chalmers University of Technology, conducting research on process systems engineering with a particular focus on biorefineries and industrial symbiosis. So Stavros, as I mentioned earlier on, unfortunately, I can't give you control of the slides for some reason. So please just tell me when you wish to go forward. Thank you.
Thank you, Simon, and good afternoon to everyone. In this part of the presentation, I will present more or less what is the current status and the potential for the current status of the cost of the conversion processes, of the production cost of the conversion processes, and what is the potential for decreasing this cost in the future. Next slide. The pathways that we have analyzed within the Advanced Biofuel project, they refer more or less to two different types of processing, thermochemical and biochemical ones, with a list of intermediate, with downstream processes and a list of final fuels. Some of them could be characterized as drop-in fuels, like the liquefied biogas. Some of them are not themselves drop-in fuels, but the mixtures with fossil fuels are currently considered drop-in fuels, like ethanol mixtures or kerosene mixtures. Next slide. So we started with an analysis of what is the current production cost of these technologies, of these conversion technologies, based on what has been reported in literature, based on our experience in Sweden from the Gobi gas plant that was mentioned also before by Ayla. More or less, this depends on a number of factors that not all of them are technical factors. This means not all of them refer to efficiencies of production and so on, but also they refer to how you do the techno-economic analysis. And that's why here in the analysis we don't have point values, but rather ranges. and the ranges are also not very narrow. They are wide ranges. The reason could be because of different factors in the techno-economic analysis, but also because of different literature sources. Yeah, there is a wide list of literature sources mentioning different costs. However, what you can see directly from this graph is that there is a certain gap to the current price of fossil fuels. And I don't mean just the very low price of fossil fuels that are perhaps under some special conditions like those that we are living right now, but generally even under standard scenarios for pricing of fossil fuels, there is a certain gap in the current status of production cost of advanced biofuels. Next slide. And we focused a lot on the capital cost potential of decreased potential of the capital cost in the future, and not in the overall production cost, because one big part of there are mainly three parts of the production cost: the capital expenditure, the operating expenditure that refers to feedstock, and the other operational cost. These are more or less in a ratio of 40-40-20. So the feedstock cost is important, as important perhaps as the capital cost, but there is not a lot of room in most of the pathways. There is not a lot of room of improving this feedstock cost through more efficient production, more efficient utilization of the carbon atoms. So what can be done in the feedstock cost relates a lot with the biomass price, which perhaps has to do with efficiencies on the biomass cultivation, but also on policies with respect to the biomass price. So generally non-technical aspects with respect to the biomass conversion. On the other hand, the other operational cost, which is about approximately 20%, they could be improved through technical learning and through more advanced integration in bigger facilities and bigger scales. But the capital cost is more important than that, and as mentioned already in Ayla's presentation, it covers 40%, and it's worth to see what it's worth seeing how much can this actually be reduced by building more and more plants, so by increasing the installed capacity. We have analyzed a number of scenarios. I show here a scenario where you are starting right now from a capacity of an installed capacity of perhaps some hundreds of megawatts, and in order to meet the targets of the future, like those that are mandated by 20%, for instance, 20-25%, for instance, of advanced biofuels in future transportation mixes. This means some hundreds of gigawatts in production, which means in turn that if so many plants could be installed, these are some thousands of plants of large-scale production. Large-scale in this case means some hundred of megawatts each one of these plants. If this scenario is achieved, then perhaps you can think about that after 30 or 40 years, the next plant that will be made will be 40% lower in capital production, in capital expenditure compared to now. But this again should be seen as a real upper theoretical limit, as a real upper bound of what can be expected in the decrease of capital expenditure. For instance, this morning in the media webinar, we had a presentation of Clariant about the plant that also Ayla mentioned that is currently being built in Romania, second generation ethanol plant. And it was mentioned that the capital expenditure is more than 100 million euros for a plant of approximately 50,000 tons per year, which is approximately 50 megawatt in this scale. This is roughly translated to a cost of 2,000 to 2,500 euros per kilowatt of product of ethanol, which is in line again with these values presented here. How much can this be increased? Can be decreased? It will depend on how many plants they will be made, and also how much bigger these plants would be. And there are, of course, also some certain limitation on the supply part of how much you can increase a certain plant size. Next slide. Another factor that contributes to decreasing the capital cost and the operating cost, but also the capital cost, since we're talking about this, is if you can make use of existing infrastructure, and there is potential, there are possibilities, technical potential to do this. And you can even start from some stepping stone of utilizing current plants that are not that cannot be thought under the current technology to be immediately or in short term turned to biofuel plants. But you could establish a certain biomass supply by using biomass in these plants to replace the fossil fuel even for thermal production, with the goal that later these plants are turned into biofuel plants. But there are also some current opportunities to increase the use of to utilize the potential of certain oil refineries that could, for instance, make use of pyrolysis oil that was mentioned before in mixed or co-processed in some allowed mixes under the current technological options with fossil-based oil, or syn-crude in gasification, syngas coming from gasification to be co-processed with syngas coming from fossil fuels. There is potential of doing that, and this can, in fact, further decrease the costs, the capital costs and the operating costs, in some cases between 10 to 40% even. Next slide. So the take-home messages is that there is a certain gap. The certain gap is estimated to be between the production cost and the current fossil prices is estimated to be between 20 to 40 euros per megawatt hour of product. The feedstock cost, which is an important part of the production cost, it's important to lower this part, but we also have to think that there will be competition in the future for biomass, and this may affect of what we believe that is the current price of biomass. Of course, there may be also technological improvements in how you cultivate the biomass and increases the efficiencies there. In long term, there are some of the current pathways, not so much the thermochemical ones, but mainly those that are referred to utilizing biochemical byproducts like lignin fractions or CO2 coming from that can be easily captured from biogenic production of for biochemical production of fuels. There is a potential for technical improvement there in order to increase the efficiencies. The point that I was trying to make for the capital expenditure is that it remains right now a certain hurdle, and it is high capital cost always involves financial risk. In the example of Clarion that I mentioned before, the 100 million euros that were requested for building up a greenfield plant in Romania, they certainly don't come all of them by just capital from the company itself, but there must be more than one capital sources utilized to start the first of a kind plants. Next slide, which is the last one also. So in short to mid-term, there shouldn't be we shouldn't believe that technical improvement alone by increasing installed capacities or other technical improvement will be able to totally, and just these alone, to bridge the the certain gap that exists now between fossil and advanced biofuels. It will contribute, but it's not going to be the main factor, so we shouldn't believe that. And at an initial phase, for the first of a kind plants, you have to have a stable environment that should be based on certain policies. No matter what are these policies, penalization, of course, of fossil fuels, subsidies coming from feed-in tariffs, or whatever policies. I think my colleagues will mention these policies later, also in more detail. And it shouldn't believe that after a certain period we could withdraw from these policies because the biofuels will be directly competitive to non-penalized fossil fuels. A certain penalty of fossil fuels will always be on the table and should always be on the table. And it's logical because this is environmental motivation that we're mainly targeting for biofuels production. And as I mentioned, after installation of hundreds or thousands of plants, we could foresee a capital expenditure decrease of 30, 40, 50% as a maximum of what can be expected, at least based on what we know now. Thank you very much. And the last slide, next slide is, yeah, okay, let's start.
Okay, thank you very much for that, Stavros. So, well, I think the key message there is that the conversion processes themselves, the technological side is not the major issue. A lot of these are proven already. It's more related to scale, cost, access to finance, and the broader enabling framework. We haven't had any direct questions to you for clarification, so you must have been very, very clear. But I'll say it again to the attendees. You can ask your questions at any point, either directly following up to presentations or for the panel discussion at the end. So thank you, Stavros. So now I will invite back once again Ivan Vera Concha. As already presented, Ivan is working at the Copernicus Institute of Sustainable Development at Utrecht University. So sustainability is one of the main concerns and challenges facing advanced biofuels. It's one that's certainly attracted not only political focus, but also a lot of popular focus. So Ivan, please, the floor is yours. I'll mention also that we've had a question come in, which you have seen, related to the use of marginal lands. So I know that you will try to tackle that now in your presentation. Thank you very much.
Thank you, Simon. Thank you for your words. So yeah, so now I'm gonna present the work that my colleagues and I did related about sustainability along the supply chains from advanced fuels. This is a combined work from several colleagues from Utrecht University, and I will be presenting for you today. So ensuring the sustainability along the value chain is one of the key factors for a successful market development of RES fuels. However, given the market for these renewable fuels is still very early, still in its infancy stage, it is important to address several topics. So first, we need to assess the current sustainability framework with sustainability criteria and certification. We also need to provide recommendations for criteria and possibilities for a harmonization to demonstrate the sustainability performance of these RES fuels that we've been talking about. We need to explore what are the potential environmental benefits and also risks from the production of these lignocellulosic biomass feedstocks, also from the RES fuels. And then we need to assess also the greenhouse gas emissions and socioeconomic performance along the whole supply chain, so from cultivation to end use. And in this presentation, of course, we will discuss the most important outcomes that we have carried out in this project. So insights into sustainability performance have already been presented in the morning session and before by my colleague Ayla, but I want to focus on the barriers that we need to overcome in order to be able to perform and to deliver sustainable advanced fuel. And these were the ones that are identified in this project. So as you can see, they are divided depending on each stage of the supply chain. And it comes from a lack of harmonization and regulation of sustainable farming practices for residues, mainly like residues from agricultural residues, also forest residues, but also for lignocellulosic energy crops, and lack of harmonization in forest management. We also found a distortion of biomass trade due to diverging national schemes between individual member states or other trade partners. We also found a lack of harmonized criteria between different bioenergy sectors, for example, power, heat, and transport. But possibly also it will be a problem later with bio-based materials produced in multi-output biorefineries. And finally, we also found a lack of harmonization between global sustainability requirements for international sectors. So now I want to share with you what are the main insights that resulted from this research and stakeholder consultation to overcome these barriers. So within the ADVANCEFUEL project, we compared sustainability criteria of the Renewable Energy Directive with the most relevant voluntary schemes and national verification schemes that have been used in the biomass and solid biomass sector in the European Union. We also identify key sustainability risks and concerns based on literature review, online surveys that also my colleague Ayla described before, and also we did a stakeholder consultation through interviews. So our main findings are that we found RED II is a major step in providing a harmonized sustainability framework for bioenergy. However, we're still meeting some sustainability criteria that need to be included in all the bioenergy supply. These criteria include other aspects of social or economic criteria, as well as more strict criteria in the sustainability, for example, from forest management. Even through a broad set of criteria is recommended at the same time, there are necessary burdens or barriers to bioenergy development that should be avoided. For example, voluntary schemes that are tailored to specific supply chain requirements, and this should be flexible enough. And finally, our stakeholder engagement. One of the main conclusions of the stakeholder consultation was that there's need to be transparency in the markets as well as sustainability reporting. And there, of course, we need clear guidelines definitions from all the supporting members and scheme owners in the implementation of the sustainability criteria of the RED II. So within the ADVANCEFUEL project, we did a case study to, as I was already showing you before, what were the environmental impacts, available land, and biomass potential of lignocellulosic energy crops in the European Union. So to do this, what we did was sticking to the RED II criteria, and here you can see how the RED II criteria translates into land constraints. So because this assessment was done spatially explicit for the European Union from 2020 to 2050. And I will share with you some of our main results. I will not share all because of the lack of time, but I want you to show basically how all these sustainability criteria from RED II is translated into land constraints. So you can see we had to exclude protected areas or Natura 2000 areas. We had to exclude high nature value farmland. We had to exclude high carbon stock areas. That's for example, wetlands, forest land. We had to exclude also natural grasslands, areas with high biodiversity index. We only could use the we could only dedicate for the production of these lignocellulosic crops abandoned agricultural land or surplus land. We also decided to include only that land that was considered marginal, according to the definition that's been given before by other of my colleagues. And what was the purpose of this is because if we include only abandoned agricultural land or marginal land, we're already avoiding indirect land use change from the competition with food and fed crops that could be potentially be displaced. So we're already avoiding a step in that potential environmental impact. So I want to show you some of the main results. So here you can see a graph on the x-axis. You can see for each year the 8 different crops, and on the y-axis you can see the tons of CO2 per hectare per year. So the emissions, and this only is related to land use change related CO2 emissions. So you can see that on average, for example, all crops are actually sequestrating carbon. But if you consider the ranges, so the ranges tell us how different can go if you produce on any specific location. And for almost all crops, you can see that despite that on average, you're sequestrating carbon, in some areas you're actually emitting quite some CO2. So for example, reed canary grass, you can see that in some areas it can overpass the threshold of 2 tons of CO2 per hectare per year, which is quite some when you then complete the whole supply chain from the production of these lignocellulosic energy crops. So now that we have seen the averages, so what is the panorama for Europe? Because we did this assessment spatially explicit. So here you can see an example of what we did. So we took one complete supply chain from miscanthus to ethanol via steam explosion. And then even if we meet RED II requirements, we still can see there's quite some variation in greenhouse gas emissions. So you can see the map for Europe. It's difficult to see on a specific pixel because the assessment was done on a 1 square kilometer resolution, but that's why we zoom in into 2 different locations so you could actually see what was going on. So the green colors represent actually carbon sequestration, so you can see negative emissions per grams, negative emissions per megajoule of ethanol, and the orange to red are emissions actually per megajoule of ethanol. So when we zoom into these 2 locations, one in Sweden and one in Spain, by producing miscanthus and then ethanol via steam explosion, you can see the huge difference. So for example, in the location space, on average, you will be sequestrating like from -15 to -20 grams of CO2 per megajoule of ethanol because of the high carbon savings you have in the land use change related emissions. But on the opposite side, if you go to Sweden, for example, you're actually emitting on average 40 grams of CO2 per megajoule of ethanol. And this is related to the land use change emissions, and mostly because of the different land use types that have been transformed in these marginal lands to be able to produce such miscanthus. Next slide. But actually, what does this mean? So if we actually now estimate which of these areas will actually be able to meet RED II greenhouse gas saving criteria. So you can see that a lot of the areas, for example, in Spain, which is the green areas, so the green areas indicate that they meet the 65% savings, and the red areas indicate that they lack to meet the 65% savings. So as you can see, for example, in Spain, all the areas that we assess, they are able to meet RED II criteria of greenhouse gas emission savings, so they will be able to actually be rolled up in the market. But if you see like in the location in Sweden, there are quite some areas that don't meet the greenhouse gas emission savings criteria. So even despite meeting RED II sustainability criteria, there are locations that will still not meet the greenhouse gas emission saving criteria that the RED II has established. But what is important to see is there's a lot still of variation, even in small areas. So even in Sweden, you can see that there's still locations that look green because they still are able to meet the 65 greenhouse gas saving criteria. And it brings us to the end of my presentation. And I want to conclude that the production of lignocellulosic energy crops in marginal lands can cover to some extent future bioenergy demand, and contribute, of course, to greenhouse gas emission savings for the European Union, but it can generate impact in other areas. So we didn't have the time to show it here, but we also assess impacts on soil erosion risk and on water use, and it can happen that there are trade-offs between impacts. That's why we need to consider smart choices on location and crop type to enable sustainable biomass production in Europe. Only this way will be able to benefit from an environmental point of view and overcome challenges of biomass availability. And also the Advanced Fuel Project provides recommendations to develop sustainability criteria and certification for advanced biofuel. And we also provide tools to measure the sustainability of biomass production at specific locations in the European Union. Thank you for your attention.
Okay, thank you very much for that, Ivan. Once again, we have no direct questions for clarification coming in, so another very clear, very good presentation. Again, don't be shy in submitting your questions. We will cover them either directly or in the panel discussion. So next up, we'll be exploring the issue of end-use performance of biofuels, looking at different end-use sectors. So for this presentation, Dr. Yuri Kroyan, doctoral candidate at the Research Group of Energy Conversion at Aalto University. So Yuri has particular expertise in material science engines and fuels, and also data analysis and modeling. So Yuri's work in Advanced Fuel has related to investigating the end-use performance of alternative transport fuels and modeling the performance of multi-component blends. So Yuri, a very technical topic, but one which will be of significant interest, I'm sure, for our audience. So please, Yuri, over to you.
Thank you very much, Simon, for your kind introduction. Ladies and gentlemen, good afternoon. So today I have a pleasure to present you the performance of advanced fuels in end-use sectors. Okay, so I would like to start my presentation with showing you the magnitude of the decarbonization challenge. In 2017, we used nearly 2.8 gigatons of oil equivalent in total in transport, included all fuels and electricity. When we look into the field, please take this blue field as the area that represents this 2.8 gigatons of oil equivalent. So when looking into the oil products, it covers this much area, so roughly all of the area, but we have still some place left for the natural gas, which is over here, then biofuels and waste, and electricity, including EVs, trains, and all other. So when looking into this shares, it looks like 96% of the energy use in transport are fossil fuels. So there is, so to say, no point in the competition between, for example, EVs and biofuels. In my opinion, they should go hand in hand, promoting each other to cover as much as possible of the black and gray field of oil and gas products coming from the fossil sources. Because on 2050, we will have at least 4 gigatons of oil equivalent in the low case scenario. So the challenge is pretty big, and we need all solutions to go together. But the fact is that nowadays we can utilize same feedstocks to produce either electricity or fuels. So we can use even renewable electricity from wind farms to produce electrofuels. We can use waste via gasification, fission drops, and so on. So the possibilities are there. And then we can utilize this electricity and fuels, of course, to power the mobility. So in my eyes, we should not, so to say, reject technologies like internal combustion engines, and but rather focus on the feedstock to bring the real change from the environment perspective. An advanced fuel project supports the commercialization of advanced renewable energy source fuels in the transport sector, and we as Aalto are the only partners responsible for the end-use part of the project. We were responsible for the task 5.4, so fuels and fuel blend properties in end-use, and more specifically, we were focusing on aviation, on-road, light-duty vehicles, heavy-duty vehicles, and marine sector. In total, we developed 7 models representing the end-use performance, so how fuel properties affect engine performance over the whole fleet perspective. And we incorporated all of those models into the user-friendly tool, where you will be able to perform your simulations in, so to say, nice environment. And as an example of the models, I would like to show spark ignition models for light-duty vehicles. So the model for the regular SI fleet is above. It represents the impact of the research octane number, density, lower heating value volume base, and oxygen content. The data are coming from various countries, different institutes, and the blacks are data from the real chases dyno runs with the new European driving cycles. The red is a model. So as we see, model is very accurate. It predicts very well the data. And what's interesting over here is that you can see that despite higher fuel consumption, volumetric fuel consumption, many alcohol blends have lower CO2 emission. And this comes from both carbon content, but also the mass-based fuel consumption, which takes into account the density. But this is the case of the regular fleet. Now the question is, what if we use same fuels in engines that are a little bit optimized, like flexi-fuel engines, that can have higher thermal efficiencies of energy conversion processes through increasing the efficient compression ratio. So here is the model that represents the effect in the flexi-fuel fleet. What's interesting is that, for example, we can see the E85 in the regular fleet that has 45 or 36, 37% higher fuel consumption than gasoline. Those two are coming from different sources, but as we see, that model predicted very well both of them. This is the difference is that some at E85 standard is pretty flexible. You can have on the upper limit of 85% of ethanol, or lower limit as low as 70%. So this a little bit defines what will be your change. But in the flexi fuel fleet, we see values oscillating near 30. And the other thing is that the CO2 emissions are further lower in the flexi fuel fleet than in the regular fleet. So we see the impact of fuel properties, but also engines itself can utilize, for example, higher RON of some fuels that have this higher RON. Due to the time regimes, I was not able to show you aviation models, marine and heavy duty, but you can find them in the deliverable D55 on advancefuel.eu website. But also, you can access our tool, online tool, with a free public access after a free simple registration. You just go to advancefuel.aalto.fi, and you can perform operations on the models that we developed. Now, I would like to stay a little bit on this table to show you our recommendations. What are good fuel candidates in our eyes by 2040 in various transport sectors? As you know, aviation is the most difficult to be electrified. So in aviation, synthetic paraffinic kerosene out of the Fischer-Tropsch or HEFA or ATG, alcohol to jet conversion, they look as the solution by 2040. Also synthetic isoparaffins, but they have lower blending wall, 10%. In both cases, the costs are high, significantly higher than for regular jet A1. The marine engines, we see that hydrogen is a good candidate. Now, currently, hydrogen is under research and development phase, but it is not technologically possible. Good thing about hydrogen is that it could be blended with methane. So, for example, LNG ships can use hydrogen, and blends by 20% are, so to say, compatible without big changes on the ship. Then, a good thing another about hydrogen is that there is no sulfur and no carbon. No sulfur is compatible with new IMO regulation with the sulfur cap, and no carbon is a good path to go for the marine IMO target for the carbon dioxide emissions, cap 50% by 2050. Now, methane, biogas, as a liquefied biogas could be substitution for liquefied natural gas. So the good thing about this is that there is no sulfur, and again, fleet operators will need to go either for scrubbers or for LNG or for methanol if it comes to the change after the new IMO regulations. So LPG could be a good solution out there. Now, I mentioned methanol. Methanol is possible. So, for example, case of the Stena, commercially proven already methanol ship. Methanol could be used as a, for example, pilot-assisted mixed control combustion. And what I mean by that is that basically we inject methanol and then we inject small amount of diesel just in order to ignite the mixture, to provide the ignition source. So methanol does not have any sulfur content, which is also very good and is cheaper than ethanol and about 50% more expensive than heavy fuel oil. Another good fuel with a little bit more future potential is biocrude from hydrothermal liquefaction. It's a promising candidate, but at the low technological readiness level, between 3 to 6, dependent on the conversion and on the feedstock. So to say, presently efficient upgrading is needed for that one. In the light duty section, we see electrification, of course, as a good way, but electrification alone will not solve the problem of the decarbonization. So the market dynamics of the every new car bought today is average fleet in 2035. We need to remember this. So in light duty vehicles, methane is also very good solution. So for example, LBG, methanol, as proven in the China, then ethanol, currently low blending was 10%, but flexi-fuel vehicles can run on E85, and they are pretty feasible to do it. Also, HVO and FAME, as we know, widely used, and of course, and nowadays, research and development in the direction of renewable diesel. So in the heavy duty, we see that methane again is a good candidate for long-haul transport, for example, in the liquefied form, in the short-haul transport in the compressed form. So good thing about methane in the light duty and heavy duty is that we can convert regular fleet spark ignition and compression ignition cars into the compatible methane compatible, so to say, engines. And methanol is also possible as an MT95, which is under R&D, pretty promising, so emissions and lower NOxes than in case of ED95. But similarly to the ED95, these are dedicated engines, so both for MT95, ED95, high compression ratio engines are needed, completely dedicated. So we face also difficulties when it comes to the infra and vehicles. So thank you very much for your attention. That would be all from my side at the moment, and I warmly invite you to the discussion.
Thank you very much for that, Yuri. We did actually have one follow-up question here for you. The question is, are regular vehicles compatible with ethanol concentrations above 10%? Well,
I would say modern spark ignition vehicles could go with, technically they could go until 15%, 1.5. But 10% is a safe limit as it is in the EN 228 standard. The problem with ethanol in higher concentration is that it accelerates the corrosion. So we need to have corrosion resistant materials, and also we lose on the performance. So when we have a little bit optimized engines that can, for example, increase the effective compression ratio by boosting the intake pressure, for example, variable valve timing or retired spark timing, it can give the bigger heat release and so to say, better effect. And of course, higher concentration ethanol can resist the knocking because of the higher RON, so we can do it from the technical perspective. But I would say 15% is top. We shouldn't try more for the regular fleet.
Okay, thank you for that very clear answer, Yuri. Thank you for your presentation as well. So we move now to our final presentation of the day before we launch into our panel discussion. I'll remind you once again that you can submit your questions at any time. Yuri, perhaps you could turn off your microphone. Perfect. So our final presentation of the day will look at the advanced fuel policy recommendations. So for this, I'll welcome Dr. Calliope Panoutsou. Dr. Panoutsou is a senior research fellow in the Center for Environmental Policy of Imperial College London, as well as being a member of the scientific board of the Bio-Based Industry Joint Undertaking and chair of the Working Group on Biomass Availability and Supply in the European Technology and Innovation Platform on Bioenergy. So Poppy, please, the floor is yours. I believe you have control of the slides.
Thank you very much, Simon. Good afternoon, everybody. I would like to go to build on the previous presentations from colleagues in the Advanced Fuel project and briefly mention to you our policy recommendations for the market uptake of advanced renewable fuels. The work has just been refined based on the latest findings. I will I'm not sure. Okay, here it is. It's a little bit slow. Policy for advanced renewable fuels, what is new? Actually, building on the discussions here and the presentations you heard before, beyond policy moves beyond Renewable Energy Directive or Common Agricultural Policy under the umbrella of the European Green Deal, which brings together an ambitional aspiration of the European Union to be zero carbon by 2050. So we will try to wrap up the advanced fuel policy recommendations around the future prospects of these fuels to contribute towards this zero 2050. As mentioned, we have followed a value chain approach. We have focused on barriers and challenges that restrict market uptake. We have co-designed most of the policy suggestions with stakeholders, and we aim to provide recommendations for optimized policy focus in the future based on competitive priorities within the value chains and the value chain stages that they include, and have an impact assessment for their expected added value. The value chain stages we have addressed in advanced fuel are feedstock production, conversion, and use. When we go to feedstock production, we have more challenges, but the major ones, because the project focused in two aspects as presented by previous colleagues. One is to have a focus on new cropping schemes and the use of marginal land. So the immediate challenge is cultivating in marginal land. Current legislation has ambitions to exploit areas with natural constraints. However, land use planning, financing, and awareness interventions are considered critical. So this means future policies should focus on refining what is already there and developing dedicated financial mechanisms that can support such exploitation. Innovative cropping systems, we need a common regulatory framework with indicators for the so-called carbon farming practices. And this will require improvements in the methodologies for data collection, for example, on soil organic carbon. And also, we do need a massive scale up. Colleagues mentioned it in their presentation, to commercialize innovative cropping systems that include biomass crops. This means that at the moment we have lack of funding mechanisms to invest in the initial infrastructures, and also to train human resources and build capacity that can facilitate this massive scale up. Of course, there are enabling policies and good practices, but there's a lot of work to be done. Our work in advanced fuel focuses on optimizing specific attributes and competitive priorities in each value chain stage. So for feedstock production, we work on land use, and we will be providing recommendations for competitive priorities having to do with the quality of the land we use, with the cost efficiency, with innovation practices that can be applied, with transparencies. We heard the direct and indirect land use chains, and we aim to also provide a quantitative impact assessment for the expected added value in terms of profitability, jobs, gross value added, and also carbon farming options for the specific cropping schemes and land use. Similarly, for the innovative cropping, we will optimize the focus for flexibility, quality, cost, and innovation, and address similar issues, but also cover the market value of co-products, because it's understandable that one of each crop and cropping system, especially if we go to rotations, cover crops, will have multiple markets, not only the advanced fuels. The recommendations under final revision is that sustainable biomass feedstocks are present in Europe, but they require to have an efficient and timely mobilization, and this is a challenge. Rural land use planning must be combined with incentives to produce biomass. There are plenty support measures around, like the structural funds, the European Regional Development Fund, but they have to be brought together in a harmonized way and facilitate the rollout of, first of all, the restructured marginal land, and also an uptake of innovations and innovative cropping that can account for carbon farming that includes biomass crops for advanced biofuels. Of course, all these need to be done together with the European Innovation Platform, the Network for Rural Development, and the European Agricultural Fund for Rural Development. When we go to conversion, we have addressed a series of challenges. The most important ones, as mentioned by colleagues, are cost reduction of these innovative technologies. So we have at the moment a generic financial options and instruments in legislation, and we need to optimize that policy to ensure that significant amounts of RES fuels and zero vehicles are deployed. And of course, these need to go hand in hand with the energy efficiency improvements. And also the element of integration into existing infrastructures requires improvement in access to finance, regulatory support, and information to SMEs and industries to facilitate the decision-making for co-location of biorefineries with existing infrastructure. With the conversion technology, we aim to optimize flexibility, innovation, quality, and of course, utmost the cost element. The recommendations are tailored financing, such as feedstock premiums, feed-in tariffs, and premiums are necessary to develop a secure framework to reduce capital investment and uncertainties. Innovations in technology development involve high capital costs, as mentioned, and thus high financial risk. Measures need to be introduced to make sure this can be covered and shared. Funding schemes, banks and financial institutions must increase budget shares for RES fuels in their investment portfolios. And very important, capacity building and public-private partnerships can help and have helped uptake of innovation in the past. So we feel that they can help tackle barriers such as those related to investor risk premium and access to debt financing. And of course, we're talking about innovation. Research and innovation is critical, and it needs to be, continuity needs to be ensured in funding for RES fuels to overcome technical barriers such as process design and scale-up considerations. When we go to end use, the major challenges are the slow uptake. We also saw in the beginning, there is a massive scale-up required there as well. The gap is the absence of a regulatory mechanism to bridge the price gap between renewable and fossil-based fuels. And future policy focus should have a market regulation with feed-in premiums, certification and standardization. At the moment, there is a very good coordinated effort in the aviation, marine and freight sectors, but they are excluded from biofuel obligatory quotas or greenhouse gas emission reduction targets and national targets. And they don't have specific quantitative provisions to promote the use of advanced fuels. So financial incentives to promote the innovation in low carbon technologies in these specific segments are also required to ensure the market uptake by 2030 and also by 2050. The recommendations, ambitious decarbonization plans require deployment of all renewable options, increase the efficiency of the transport system, and significant shifts towards more energy efficient transport modes. RES fuels are likely to exhibit increased shares, first in road transport. However, it's critical to enable a similar and timely shift to the heavy-duty fuels in maritime and aviation, which at the moment have less alternatives and are more challenging in reducing CO2 emissions. Without tailored targets, these sectors will have difficulties to cope in the uptake. Electrofuels produced from renewable electricity and direct air capture are essential to complement the contributions for the decarbonization of the transport sector, and they can be particularly useful in aviation due to a limited number of certified biofuel value chains in these sectors. Biomass to liquid, pyrolysis, co-processing must be deployed before 2030 to ensure fossil diesel substitutes are in place to meet the target stated. And finally, a few cross-cutting recommendations for sustainability across value chains. The sustainability criteria in Renewable Energy Directive 2 are a major step forward, but not yet sufficiently broad and stringent to address all concerns around. So harmonized criteria beyond are required. Definition for feedstocks, measurements at EU level preferred for the first stage. More transparency is needed in market and sustainability reporting, and there's a need to provide especially explicit and quantitative insights regarding the environmental impacts of lignocellulosic biomass feedstock production in order to have clarity and transparency across all applications and sectors. Thank you very much.
Okay, thank you very much, Poppy. And thank you everybody else as well for your presentations. So again, we have no direct follow-up questions, so I think we can go into the panel discussion straight away. We're running around 10 minutes late or so, but I would still like to keep about 20 minutes for this discussion. I will try to squeeze in my conclusion presentations at the end of the session. So at this point, I'd like to invite all of our technical presenters, so Poppy, Ayla, Ivan, Stavros, Yuri, and Sonja, to share their cameras. There's a limit to the number of cameras, so I will now disappear. Yuri, there seems to be some feedback once again from my microphone or from your speakers with the microphone, so perhaps you could just mute if you are not speaking.
Okay.
Okay, so this session will be moderated by myself, but also by Kristin. But I would like to start off actually with a couple of polls to the audience. The aim would be to get, well, some feedback from our attendees today, and then I would ask our panel to respond to the results that come in. So the first question would be, what do you consider to be the main barrier to uptake of res fuels? So high cost of feedstocks, lack of clarity regarding sustainability and environmental impacts, difficulty in accessing finance for biorefinery development, or lack of sufficient policy support. So I'll leave this poll open for another 5 seconds or so, just to get a few more responses in.
Simon, I have a little bit problem with selecting. How you select?
The poll is for the attendees only. As a panelist, you may not vote, but we will get your opinion in just a second. Okay, the numbers appear to have stabilized there. So let me just share with you the results. I hope that you can all see this, including our panel. So, well, way out in the lead is lack of sufficient policy support. So that's 48%, 24% on difficulty in accessing finance, 19% lack of clarity regarding sustainability, and 10% on high cost of feedstocks. So I would be interested in hearing now from the panel what they would regard as the single largest barrier, and perhaps also just to respond to whether you, find these results of the poll to be accurate or quite bizarre. So maybe we can go first of all just through the panel participants as they're presented on the slide. So Ayla, could we start with you?
Yeah, sure. I think the reactions are quite in line with what we have considered in Advanced Fuel project. And I could very well understand why lack of sufficient policy support has received the highest score. Currently, I mean, one of the legislations that directly influence biofuels, advanced biofuels, is Renewable Energy Directive, the recast Renewable Energy Directive, and I already introduced the target set is quite low for biofuels produced from feedstock listed in part A, and I haven't mentioned in my presentation, but within that feedstocks you have also the ones that can easily be fermented to produce biogas, and we didn't study them. So in that regard, I think the pull from the policy process is quite low.
Okay, thank you. Sonja?
Yes, I think that we somehow influenced also the opinion from the audience, because of course we tried to say that the feedstock is available if we also use the marginal land, and then in the end, of course, it's a question of policy. If we are allowed to use this land, and under which regulation.
Okay, Diva?
Well, especially I think that despite the lack of sufficient policy support got like the biggest percentage, I think still there are barriers in the four answers that we have made, and we still need a sufficient policy support, especially to what is coming and to deliver the amount of biomass that needs to be delivered, because we are in an infancy state right now. So we really need to start moving quite agile, I would say. But also by this type of research, we're finding that that even if we had already, for example, with the Renewable Energy Directive, kind of defined what was sustainable for biofuels, we are still coming to know that even if we meet the sustainability criteria, we might have not even meet their greenhouse gas emissions targets. So it's a bit of a both way that we need to consider for the next steps, I think.
Okay, thank you. Stavros?
Yeah, I would like to stay on the point of the difficulty to finance the biorefinery development. I think this is justified because we're talking about large plants here, and large plants mean that they need a big initial investment, and they need to have some market stability to be able to pay off the investment. Is not something that you think it can be paid off in a couple of years. So we're talking about plants that they need to have a certain horizon of stability of 10, 15 years, that they will be certain that they will operate under some economic conditions that are favorable. So I agree about this point. That is also relating a little to the policy. And I think that the first main players will be big companies, because they can have better access to financing under favorable conditions. But I don't think they will be able to handle the first of a kind plants alone. They need support in co-financing from other sources too.
Okay, thank you. Yuri?
So I entirely agree with Stavros, but I would say I see that policies are pretty much the drivers over there, a little bit more than financing, because refineries even would be perhaps eager to finance some capacities, to increase their capacities of renewable fuels production. But what's important is, as Stavros mentioned, long-term stable policies. These are something that has to be provided. And the other part is also changing the regulations when it comes to because this is a little bit complex problem. We have vehicle engine manufacturers, we have fuel producers, and we have end users, and we have policy that regulates this all. So when it comes to for example, CO2 emission limit 95 grams from this year forward in the light duty transportation, electric vehicles are treated as a zero, and biofuels are not taken into account at all. So, for example, engine manufacturers would be eager to go more for the electric vehicles to get carbon credit. Otherwise, they pay big fines if they do not meet this. So there should be policies that include both engine manufacturers and also fuel producers, and to accelerate this market uptake. So I think policies are very important driver over here.
Okay, thank you very much, Yuri. And Poppy.
Yes, thank you. I couldn't agree more. And I would just like to change the sufficient with 3 issues. I don't think there's not sufficient attention in policy, but I do believe that this attention is not integrated. There's no sector integration in this attention. And Yuri mentioned it, all colleagues mentioned it. These fuels require a sector integration and require it immediately in terms of policy information. There's lack of clarity that comes with this, and there's very low focus on value chain stage challenges, which actually require policy either in a regulatory form or financial support or capacity building. So I think I do understand why people turn their heads on policy, but there is attention in policy, but there's a lot to be done to refine.
Okay, thank you very much. Yes, Stavros, please.
Yeah, just to add something on policies, that was recently a point of discussion in another meeting. And it was touched a little by the presentation of Yuri. He mentioned that we have now 2.8 gigaton equivalent needs of transportation, and this is translated in the future of perhaps 30% increase to 4 gigaton equivalent. Perhaps we should put on the table policies of decreasing the future use of fuels, which means policies of decreasing our necessity to be mobile. So not only policies on the conversion part, but also policies that they have to do with the social behavior of people, that they decrease the necessity for fuels.
Yeah. I would like to add something to that, Simon, if you let me.
Of course, go ahead.
Within the integrated assessment, the scenario analysis we conducted, I didn't have time to share those with you. I said that, for instance, we introduced a target for maritime of 50%. And when we looked and we considered that technologies can increase significantly. However, at the end, the result was that with even that high amounts of deployment rates, we couldn't achieve the target, for instance, for maritime sector of reducing CO2 emissions by 50%. So the ultimate conclusion indeed was that demand side management is equally important as supplying renewable sources for the transport sector. So I very much agree to Stavros' point. Yeah.
Okay, excellent. Thank you very much, everyone. I think that just for the sake of timing, I will skip this second poll, and perhaps we can go to some of the questions submitted by the audience. So, Kristin, I don't know if you would like to go first with a question, or if I.
Okay. Yeah, I can surely do this. We received, for example, one that says, do you think we have enough time to convince the agricultural sector to invest in the marginal lands to biofuels value chains and to make this activity part of the future European CAP? So I don't know, this certainly addresses for the feedstock availability, Ivan and Sonja, but also Poppy for the policy needs. Who could be the first one to reply maybe to this question?
Maybe I can start, even though I don't have really an answer for that. But from what I found in the literature is that, whenever there were some subsidies to increase the cropping, so it worked, it increased, but the speed we would need to reach these areas would be much higher than what we have seen in the past. So just learning from the past, just doing it how it was done before, I think it's not possible. But, well, maybe others have ideas how it could be improved in the future.
Okay, Poppy, maybe something to add from your side?
Nothing more than the sector integration that I mentioned. For sure, time is always a problem. But I also agree with Sonja. The lessons from the past, probably we can learn what we shouldn't be doing. I'm not quite sure we hold the silver bullet here on addressing that issue, and to make sure, I think in this debate, you definitely need colleagues from the agricultural debate sectors, and there are many at the moment within the farm to fork and within the biodiversity strategies, but it's worth a try.
That's true.
Okay, thank you. If there were no more responses to that, we can perhaps move on to another question. I take that as a move on. Okay, so we had a question which I think is perhaps primarily for Ivan, but I think maybe everybody could contribute. The question was regarding sustainability and the Renewable Energy Directive. How do you handle indirect land use change questioning?
Yeah, so with the assessment we did, we actually, by the use of marginal land, so we already, I mean, in the RED II directive, it's already included that if you produce new lignocellulosic energy crops, so in new areas, you cannot induce indirect land use change. That's why we make use of these marginal lands that cannot be used for food or fed purposes. And you cannot produce other type of let's say first generation feedstock there, because well, it will simply not grow as well as these lignocellulosic feedstocks could be grown there. So we are already omitting the food versus fuel debate, but first of all, producing lignocellulosic energy crops. So we're not using food or fed crops to produce energy. And second, we are using land that otherwise will be not being used for any other energy purposes. However, of course, it can be used for other non-energy purposes, and of course that will mean an indirect land use change in another manner. But still, with the assessment we did, we tried to consider that the land that we will be using and the projections of lands that will be allocated for this production will be most of it abandoned land or land that was not serving any purpose, and could be beneficial either from an environmental side, so we could sequestrate carbon, for example, or could have any other benefits in the environmental part.
Okay.
I would like to add on to that you know, with an advanced fuel project, the focus has been on mainly waste and residues, and one of the reasons that advanced biofuels was promoted was that they would not have indirect land use change, and the land use, marginal land use related to dedicated crops is just one part of the big picture. So we are talking about potentials that are around, I think, 12,000 to 14,000 petajoules. So I think we shouldn't confuse the discussions about ILUC that has happened in the past with these advanced biofuels. We need to be a bit careful of that.
Okay, thank you. Sonja, do you have anything to add on this issue?
No.
Okay, thank you. Kristin, would you like to pose a question?
Yeah, the audience had been unfortunately a bit reluctant to pose some questions, or maybe it's also a good sign for the presentations that have taken place. So I don't really have an additional question from the audience side. Correct me if I'm wrong.
We had a couple just come in, including one.
Oh yeah, here.
Yeah.
It's true. So, well, I just read it directly. The attendee is asking, I would suggest whoever feels strongly about using marginal lands for biofuels production to talk to the Farming and Agro-Industries Association, such as the EBB or Copa Cogeca. So that's that Green Deal, farm to fork, also can be translated as farm to fuel. Do you agree with this statement, Poppy?
It's a nice suggestion. I'm not sure we are responsible to change names in umbrella regulations, but certainly I think, and we all are aware, these crops will be, there's a biorefining that will take place. These crops will not be only farmed to fuel, it will be farmed to products. So they have to be multi-product, multi-end use. It doesn't make sense to, and again, I go back to the integration and to make sure there's clarity that the natural resources shouldn't be depleted. We should respect the use of land, water, and also the knowledge of the farmers, and try to offer them opportunities instead of fragmenting them further and confusing them. So if it was for me, it would be farm to markets and farm to opportunities. It wouldn't be farm to fork or farm to fuel per se. It would be farm to opportunities for rural development and European farmers. But I fully support the fact that diversification and looking into future prospects of different products and co-products. Similarly to co-location with existing biorefineries, you can have co-production through crop rotations and different innovative cropping systems, and I think we have addressed them well in the work presented by colleagues in ADVANCEFUEL.
Okay, thanks a lot for your opinion. Simon, another question?
Yes, actually, so I have one that's not been asked today, but I had received quite a few emails in the run-up to this webinar, and quite a few of them were relatively skeptical about the potentials for advanced biofuels. I had a couple of emails saying quite simply stating that they did not think that the 3.5% target was remotely realistic, expressing the opinion that Europe was being led up the wrong path by trying to reach this target. I'm just wondering if anybody would have any reaction to that, and would be, well, perhaps willing to put their reputation on the line by telling us the chances they think of us reaching this 3.5%. I'm looking at Ayla here, who's been very quiet.
Yeah, that's correct. I was wondering where this reaction comes from, to be frank. I mean, one of the things that I mentioned was the target set 3.5% is not the real actual target. Actually, it's an administrative target, and the real target in energy content is 1.75% target. So it is much lower. Let's first make it clear. And second, this target refers to a set of feedstocks in a list, and as I said, that set includes lignocellulosic feedstocks, which require technologies that are, let's say, in early stage of development, whereas still lignocellulosic ethanol production, for instance, is being commercial. It's at the verge. Gasification has been happening, but on top of that, you have feedstocks where you can make biogas by fermentation, and it's a commercial technology that has been happening, and then from there you can just clean biogas and make biomethane, bio-LNG, bio-CNG. So I mean, I do not agree that the target is high, and I do not agree that you know, we are putting the industry to a wrong direction, because I try to explain that if we take the Paris Agreement goals, you know, limiting global warming, global increase to below 2 degrees Celsius, we are talking about even 1.5 degrees Celsius. We need tremendous efforts, and you cannot do it in the last minute. And as I said, I mean, the numbers, I didn't have time to explain them in details. I just talk about the biofuels part, but for the electrification, both direct electricity or in the form of e-fuels or hydrogen, the renewable electricity that you will need are extreme. Even they can become higher than the net electricity consumption in Europe. So, I mean, these needs to be done. And if, I mean, as I said, I don't know where the question comes from, but it's not only advanced biofuels. In my opinion, all options, including conventional biofuels, provided that they don't have, you know, significant negative effects to the environment, that they don't have ILUC issues, they also have a role to play. But all renewable supply options need to be deployed, and we are talking about 30 years. Yeah.
Okay, thank you, Ayla. I'll tell you where the question came from after the webinar. Does anybody else have a view on this? Anybody else? Or we can go to, I think, the final question.
Perhaps the only thing I could add is that this 3.5% translates differently in national targets. Because different countries within Europe have different potential to realize this, and this should be taken into account into the discussion.
Okay, thank you very much, Stavros. Okay, so the final question, I think, before we close the panel discussion, is quite a technical one, and if we can't answer it, we can't answer it. But the question was, what does the panel think of the move by the Federal Republic of Germany to outlaw the retail of synthetic fuels XTL, according to EN 15940, the standard under which Fischer-Tropsch fuels and HVO fall?
Yes, that's certainly a question to Yuri. Yuri?
I think so.
Yeah.
Yuri, any response?
Do you have an opinion of this?
Can you hear me now?
Yes.
Yes.
Now
I was muted by the organizer because of this microphone issue. So Simon, could you please read one more time a little bit slower the question?
Certainly. So it was, what is your response to the move by Germany to outlaw the retail of synthetic fuels XTL, according to EN 15940, the standard under which Fischer-Tropsch fuels and HVO fall?
So they move out of this or towards this? What was the beginning?
So what does the panel think of the move by Germany to outlaw the retail of synthetic fuels?
Outflow the retail of the synthetic fuels.
To outlaw, to ban.
Well, what I think, yeah.
Excuse me, Yuri. Apparently, I mean, we haven't heard about this. This is for me at least the first time that I'm reading that there is such a regulation in Germany to outlaw. Yeah. And it says the move of the Republic of Germany to outlaw. Okay, I don't know.
I also haven't heard about this, but what I can say is that, for example, hydrotreated vegetable oil is basically an excellent drop-in substitution for diesel, which can be basically substituted fully with 100%. And what this means that it can satisfy the current fleet of diesel vehicles. it is difficult to find better fuel than HVO for light-duty transportation equipped with diesel engines, I would say. Because FAME, fatty acid metal ester, biodiesel, above 7% causes various engine-related problems. So to have like real drop-in fuel, HVO, and this kind of Fischer-Tropsch fuels are, I would say, the best solution.
Okay, thank you, Yuri. We did receive some additional information about this from the questioner, but I would suggest that we follow this up by email just for the sake of time. So with that, we can call time on the panel discussion. Thank you all for taking part there. You are free to turn off your cameras and microphones and relax.
Thank you.
And
Thank you very much.
Thank you. Okay, so before we finish today, I just want to point the attendees towards some sources of further information, which may be able also to answer some of the remaining questions. Basically, in order to make the navigation of our results a little bit easier, we have developed a final publication, which you can access via the control panel in the handouts, but it's also available on the project website. So this brings together the key messages of the project, as well as pointing towards the relevant deliverables where more information is available. Additionally, to make the results a bit more accessible for a more sort of non-technical audience, we've developed a visual journey. So it's a digital photo exhibition integrating infographics and statistics, which can also be used to further explore the project. So this can be found at the project website under the Tools tab. As well as these two final outputs, you can of course also check directly all of our deliverables and some of our publications, including fact sheets and scientific journal articles. These can also all be found on the ADVANCEFUEL website under the Publications tab. So plenty for you to explore if you are still interested in the topic. And whilst this today has been our final event, it's not quite our final event. So I'll briefly hand over to Kristin to talk about some of our remaining activities, as well as to get her closing words.
Yes. Thanks a lot, Simon. Yes, as this Corona pandemic, created a lot of confusion also for our project work, and which ended up in organizing this webinar instead of a live event in Brussels. This also changed the plans for the UBCE, which some of you might also know. And that's why it make appear a bit weird to have a final event before the last dissemination work of our project team. And but nevertheless, it's like it is, and that's why I would like to make you aware of one of the last presentations, which will be carried out in the framework of the UBCE, which will be a digital version as well this time. And this will actually take place from the 6th to the 9th of July, which is already in 1.5 weeks. And we actually have several poster presentations there, which shows results from Aalto University, from Utrecht University, and also from the Chalmers University. And we have on the 8th of July some oral presentations as well, showing for instance, Ayla with a systemic analysis of renewable fuels, but also from a representative from Utrecht University who gets a bit more detailed about the sustainability criteria and their standardization. So maybe you can have a look at those presentations as well, as I said, in the frame of the UBCE. Yes, this is, I think, one of the last dissemination events before our official end of August. Before I will say my farewell to you and thank you very much for the participation in the webinar, I also want to thank you very much, say a special thank you to the stakeholders that have followed Advanced Fuel through its lifetime. Like our advisory board, which consisted of Ingvar Lande, Philippe Marchand, and Eric van den Heuvel. That was a very, very, very supportive work. We received so much help from your side and your experience, and so thank you very much in that regard, but also to the other stakeholders that registered in our stakeholder platform who took part in our consultations. This was, as I said, very helpful to receive validated results, and which help to really deliver some high quality deliverables, which you hopefully check out on Advanced Fuel's website, as Simon has mentioned previously. Okay, so that's it from my side, again, thank you very much for attending and for posing some additional questions, and goodbye from my side.
Okay, thank you very much, Kristin. I can only repeat what has been said. Thank you to everybody for participating, particularly those brave souls who have stayed on to the end. We've overrun slightly, only 15 minutes in the grand scheme of things. I think that's pretty good. But yes, thank you for joining us. As I've said again, and as Kristin has said, please do look at the project website. It's here on the screen in front of you. A lot more information for you to dig into. So thank you again, and let me wish you all a good afternoon. Goodbye.